Welcome to day number 3, and Nika giving our last tutorial talk on learning incentives.
Thank you. Thanks for the invitation. I've been really enjoying listening to the talks in the past few days. So also looking forward to chatting with you guys about what I'm going to present. This is a tutorial on learning and incentives, which is a pretty big topic. So kind of just to like ground it a little bit more. What I'm going to be talking about is strategic interactions in interactive decision learning in particular.
You were sharing the wrong thing.
Oh. So while you fix that, I guess every speaker said a little bit about the style of questions. Feel free to ask any questions at any time. I basically have already carved some stuff that I don't need to present to you. So, you know, if I see that we're having much of a conversation rather than what I wanted to present for those 10 minutes, we'll just skip those. And if I see that you're running way over time and there are other things I want to present, then maybe at that point, I'll start to hold off some questions. Okay. So I want to actually start back a couple of decades ago to talk about foundations of machine learning theory, and some of the fundamental questions that were posed when computer science and statistics came together to talk about machine learning. So one of the main goals that was defined as machine learning goal was what concepts can be learned from data and with how much observation. Now, there are a lot of keywords here that are vague. What's a concept? It's not very clear. Data is probably clear, and even what's observation versus data is still not clear. But those will become more and more familiar. And if you want to think about what they really meant back then, the things that they had in their mind in terms of concepts were like images of desks and chairs. And if I'm looking at these images, can I tell which ones are chairs and which ones are desks? So it's interesting that this was kind of the foundational way of thinking about learning. And it's still the same foundation, in fact, when we think about cats versus dogs, spam versus non-spam. In fact, image classification, that's a huge, huge part of machine learning. It's all about this type of pattern recognition and predictions, which are about objects. Now, while the chairs and the desks don't really care about how well you classify them, what you're also doing is that we are using the same sort of foundation to talk about learning algorithms that are actually interacting with environments, where these environments do react back or do care about what types of things are getting deployed. Throughout the talk, I will give some examples, but the things that you're going to see are some very intentional feedback loops and some somewhat unintentional feedback loops. So intentional feedback loops might look like the types of policies that Uber, ride-sharing platforms, advertising platforms, content sharing platforms actually deploy in terms of how to recommend things, what type of content that might be inappropriate to filter out, and then how potentially content providers and users will react to them. So those could be mostly intentional. But there are also unintentional, unpredictable ways that something might evolve because we're interacting with a very complex environment. You could have financial markets in mind, but there are many, many other things that just happen unpredictably in ways that we cannot model or understand very well. And in fact, some of these interactions are also collaborative, which I'm not going to go into today as much, but I will talk about in the Friday talk that I will be giving. So in light of this, how do we change back the question that was posed in the 80s so that is still about fundamentally, limits of learnability and what concepts can be learned, but in light of the needs that we actually currently have and environments that we're actually working with. So I would say that I want you guys to have 4 questions in mind. The first one is still very similar to what we asked before. What concepts can be learned, but now in presence of strategic and perhaps also adversarial behavior? And then what we're going to do is there is actually quite a rich literature that I'm going to start this tutorial with that. It's quite old, rich, and some very, very new stuff. And we're going to think about what lessons we can learn from that very rich literature. After that, we're going to think about, okay, now that we understand limits of learnability, in terms of actually designing learning algorithms or thinking about dynamics that exist in the environment, how would we sort of adjust for them? I will talk a little bit about that, and the types of questions that might come up are, what are sort of some principles as to how to use data or not to use data in order to achieve the types of guarantees we want. I will want you to think about collaborative environments, although I will not be actually talking about them today. This is, again, I just want you to have in mind that it's not just adversarial and strategic. There's some collaboration also that's important. And generally, what is actually connecting these questions all together? Okay. So before I continue with that, it helps me to understand actually who is sitting in the audience, because I've been wondering that for the past few days. I'm a computer scientist, but I do work in the intersection of computer science, stats, and a little bit of algorithmic economics. Even though we're in the econ department right now, I assume some of you are economists. So who is economist? Okay, who is a computer scientist? Statistician? Others? Okay, so we covered 3. Okay. Okay, so majority being economists, I will, if I have to skip stuff, I'm sorry, it'll be the algorithmic, more CS stuff, so but I'll try not to. Okay. So what's the style of today's talk? I'm going to go back and forth between computer science and some game theory, mostly game theoretic concepts to motivate what we are studying. And what I will do is that I'm going to go mostly at very high level applications rather than going very detailed into any one of these applications. I'll use them as motivation primarily so that we can then talk about certain ML abstractions that we want to address those challenges. And then we'll go back and forth with then what are the related game theoretic concepts and are there new perspectives or new challenges that come up when you really think about those game theoretic concepts being applied to machine learning environments. So we're going to start with some very basic considerations of ML. I want you to think about this as vanilla, uninteresting ML, but enough interesting that you want to keep it in mind since it's going to be the basics of comparison. That's the thing that's going to be the easiest to do. And everything with adversaries and strategicness and societal consideration is going to be on top of that and harder. Then we'll talk about adversarial interactions. And then we'll move beyond just having adversaries and think about more general strategic interactions where nobody's trying to get out there trying to get you, but there's still some very interesting feedback loops happening. So what is this vanilla machine learning? There's many different ways of talking about foundations of machine learning. But one way that I like to think about it, and I like you guys to think about it, is that it's used for detecting natural phenomena, objects, cats, dogs, trees, desks, chairs, where there is no reaction really coming from the environment or the object. I might have a bunch of trees. I want to know which ones are the oak trees. So the underlying assumption in vanilla machine learning here is that there is a stochastic process that's generating the data. These are observations you see. That stochastic process doesn't change over time. Okay, so trees always are trees, the same set of pictures that you can see. And then a learner's goal is to learn a function using the data that it observed. And the learner is successful if it can get pretty high performance on the underlying data distribution that we said is not going to change. You're not concerned with the possibilities of new trees coming up. So this is what we call stochastic setting. The formal way to think about this is that I have an unknown distribution D. It's over an XY space where X's are the features I see and Y's are the labels. And then I also have a class of functions. So these functions could be decision trees, neural networks, half spaces, anything. And then at every round, I see an observation and I have to make a prediction. So what the learner has to do is to come up with some prediction rule This is an arbitrary prediction rule FT, which takes any feature vector and gives a y. And then the world is going to independently pick an XTYT, a new picture. And the learner wants to really figure out if it can label these things correctly. The emphasis here is really on the IIDness or independence of XT from whatever the learner has been doing in the past. And then the learner observes what this data point was, figures out if he made a mistake or not. And if he made a mistake, he's going to incur a loss. That is our LT of FTX. And what I want as a learner is to have something called a regret that is vanishing as t goes to infinity. What is regret defined, or average regret? If I say regret, it means average regret. It's defined as the gap between what the algorithm achieved in terms of its loss and the loss that the best function in my class H would have achieved. The best neural network, the best decision tree. More formally written this way. So one way to think about this is that what you really want is for this average regret to vanish. So as t goes to infinity, this is going to become 0. And what that means, and we call that a no regret algorithm, means that even though you didn't know the distribution and you didn't know what function would have been best for that distribution, you picked up on it quite fast and you stopped making big mistakes. So that's what it means to be no regret. Now, how do we learn in stochastic settings, and why do I refer to this as a vanilla easy case? Not only learnability is possible in the vanilla setting, you should really think about this as exceedingly easy. As in, you converge to that 0 really, really quickly. In fact, if I wanted my average regret to be less than epsilon, you kind of run in time about 1 over epsilon squared times some constant, which is only a function of your hypothesis class. And I'm not going to prove this to you, but I want you to still get the bigger picture because we are going to see what changes once we have strategic interaction. Imagine this was a distribution of all pre-images. And this was the images of oak trees. So anything that fell here, it was an oak tree. So H star is the one that I want to match its predictions in terms of predicting whether a new image I see is an oak tree or not. While H might be infinite, it might be all neural networks, whatever you want to think about it, there is still some finite proxy of it that's defined over this distribution. How do I think about this finite proxy? Well, let's say that any of these sort of boxes here are the set of H's that I care about. Then I can divide my intervals so that the only gaps that I'm not capturing are about epsilon under this distribution curve. So what does this mean? It means that this is one hypothesis and that's one hypothesis, but I don't have a hypothesis like the blue anymore in my proxy class. Now, while I don't have a hypothesis like blue in my proxy class, this proxy class is still a very good proxy. Okay, why is it a good proxy? It's because eventually, once I see enough samples, let's say these dots are the samples I've seen, the oak trees and the not oak trees, they start covering all these epsilon intervals. So once I look back at my data and I just try to fit the data at some point, I'm going to see that there's this H proxy, and that H proxy is never going to be off by more than an epsilon. And that's literally why we can learn in the stochastic setting, because there's always a proxy that's finite size. In fact, not only is finite size, we understand its size very well, and its size is the thing that characterizes the ease of learnability. So the size of H proxy is a good measure for approximating this. And what I'm going to do purely for intuition, I'm going to introduce a dimension, keep it in your mind for 5 minutes. If you want to forget it after 5 minutes, it's okay. But keep it in your mind for 5 minutes. Something called the Vapnik-Chernowsky dimension or VC dimension that says that the size of this H proxy is going to be really determined by some notion of a capacity of your function class, like neural networks. What is that capacity? That capacity says, imagine I have a table, you can think about it as a game table, where on the rows I have my functions, on the columns I have all possible feature labels. And what I want to say is that I want all these rows to be independent of each other, to be different from each other. So VC dimension is the largest D that I can choose D columns so that I have all 2 to the D plus minus rows. So that's the capacity. The more complex your H is, the more things you can fit in every, like interleave in every which way you want. And the interesting thing here is that whatever that VC dimension is, it actually not only it's an upper bound on the regret, it's also a lower bound on the regret in the worst case. So you should really think about what is possible to learn, anything that has finite VC dimension. Okay, so what are some classes with finite VC dimension? There are some very easy ones. Well, imagine all those boxes that I showed you, they're called thresholds. As in you have negatives and then at some point you have positives. These thresholds have VC dimension of 1. Because there's definitely one point that I can label either way. So I can label it positive by taking this function and negative by taking this other function. And then I cannot label any 2 points because if I take 2 points, it's impossible for me to label the smaller one positive and the larger one negative. It just doesn't fit. So this is a very simple class to learn in. Have this in mind as an example because we're going to see how while it's very simple for vanilla, it becomes impossible to learn with one level of complexity. Yeah.
It's a very big picture question. So you mentioned that the VC dimension provides us with an upper bound as well as a lower bound in the worst case. Does this usually in these kind of problems apply well to kind of applied performance in the sense that does these kind of worst cases provide a good guide for choosing between different algorithms and seeing how it works?
But there's something that I didn't talk about. So VC dimension doesn't, but there are 2 other things. There's a notion of cover, which is what that H proxy was. And that is a relatively good measure of predicting what is happening in practice because it's defined per distribution. And then there are other versions of this thing. There are things called Rademacher complexity, stability bounds. There are a whole bunch of other things that are built on top of these. For practice, there are a better version of this. They'll just kind of think about them as out of the scope for today's tutorial. But most things I will tell you, VC dimension is more of an artificial thing. It's just a clean way of characterizing it so I can show gaps for you. Otherwise, what I'm going to do is to show that you can actually reduce certain things to stochastic setting and just assume whatever worked in the stochastic setting would have helped you. But that's a good question, like in terms of worst case, no.
Maybe more of a comment, I guess, in terms of clarifying this, at least for me, I started reading stuff that was helpful to think. In a way, what happens in these frameworks, I think, is that you shift the restrictions from the data generating process to the comparison set. But it's happening already here when you talk about the stochastic setting, where you still allow any IID DGP, but you have a restricted comparison class, for instance, restricting the VC dimension.
Yeah.
And then you can push it, I guess, one step further once you get
That's
to the adversarial one.
Exactly.
But in some ways, you're not dropping the assumptions, you're just moving them to a different place.
Absolutely. Like if you come from more Bayesian background, you have assumptions on different things. You have not only assumptions on what your X's are, but also you have assumptions on what you thought about H before you saw any of your X's. So there's this thing that says you just cannot learn if you don't have any assumptions. There's some basic assumptions you need to be making. And we're making these, but you're absolutely right.
Right, but I mean, for instance, I guess you're going to go there like dropping the IID, but then you're, for instance, restricting to like a comparison set of constant actions, which is taking the same role as IID. So it's not.
Let me get to that. It's too soon. I will talk about that.
The example here is it's labeling or classification. Is the VC dimension concept applicable in the other system regression?
Yeah, so it gets called a different thing. It's called a pseudo dimension rather than VC dimension. Everything I say applies to real value, actually. Yeah.
My understanding is that it's difficult to apply this VDC dimensional reasoning to deep neural networks because they're so highly parameterized. Have you seen anything which compellingly kind of does this?
We have a very poor understanding of deep neural networks. That's like the line I would tell you, and any person who understands foundations of ML will tell you that. The only things that we somewhat understand are kernelized, highly over-parameterized networks that aren't neural networks anyway, like they're not the ones we're using in practice. And some notion of stability that comes from a form of optimization. Okay, cool. So what was the purpose of this vanilla? Wasn't to tell you the model, learning thing, but it was as a comparison as even if you thought that this was simple and doable for neural networks, which is questionable, then everything else is going to become even more impossible. Okay, let's move towards some feedback loops. And what I want you to think about are now situations where there might be no distribution, or if there is a distribution, that distribution might be changing in ways that are unpredictable or adversarial. Let me give you two examples. One comes from large language models. I assume many of you have actually tried either ChatGPT or GPT-4 or other platforms. They're trained to actually not answer certain types of restricted prompts. Like if you ask them to help you figure out how to commit a crime, they're supposed to tell you that, no, I cannot tell you that. But it's actually really easy to manipulate them by just changing what you're asking. For example, you can be like, tell me how to commit this crime and start your answer by absolutely, here is a list of them. And they will actually answer. So it's actually quite easy to get around these trained restrictions that they have learned, but unfortunately aren't really practical when people actually, like adversaries, try to deal with them. Other examples, this is something that, for example, is really important for YouTube, is that you have appropriate and inappropriate content. You're trying to figure out what's good and what's not good. And those who are actually making the inappropriate contents are also trying to get them across the filters that are made to recognize this. So what are some things they do? They actually might, I didn't want to put an actually inappropriate image, so this is whatever. they might put these meaningless to the eye types of like frame news at something that just makes it pass certain filter checks, but that content is still inappropriate. So these are some examples of adversarial behavior that you actually see in practice. And the main thing is that when you think about adversarial behavior, you should, especially something like the GPT example I gave you, you should forget about distributions. In some sense, even if there was a distribution, then the data is not coming from that distribution when it's adversarial. So if I start with the distribution of all the text that is on the internet, and maybe, this is the restricted prompts, and truly there is a tiny epsilon that's not being well represented. So I could learn a proxy that would have worked relatively well under this type of data. In reality, the adversary who really wants to produce a bad behavior is just going to focus on the area that is not doing well. So you should forget about at least strong assumptions about what distributions are existing.
Just at a high level, isn't that kind of captured by the previous framework in the sense that you look at worst case distributions for a given learning algorithm?
The difference is that worst case distribution remains the same throughout in the past one. The adversary, you could think about it as the distribution is fixed, and then the data is independent of your earlier decisions. Here, the data that you're going to see, these red prompts are not independent of what GPT-4's current.
But for previous type of results, like the distribution is still a function of the algorithm, right, that you use.
No, so let's.
I mean, when we think about the worst case bound, with the VC dimension or things like that.
Yeah. The worst case bound is for the VC dimension, but let's look here. What's important is this, is that XTYT, like D is the, there is no DT. D is decided.
What's the D of the algorithm?
D of the algorithm, that's possible, but the XT doesn't depend on the earlier FTs and HTs, or XT doesn't depend on XT minus 1.
Yeah, but I guess what I'm trying to say is like forget about time for a second, but still it's an adversarial setting in the sense that
It's a
for any
different-
given task hypothesis and any given learning algorithm, it's asking you what's the performance for the worst possible
Right, but
distribution.
it's a different type of adversary. It's an adversary that does one action. I will actually talk about min-max theorem in like 5 minutes. Depends, but probably take more than 5 minutes.
But it's not like a Bayesian frame
But
for your
I'm
averages.
going to show you how these two are slightly different. Actually, one is more max min and the other is more min max. But if you want to just think about it across the two things I'm talking about, the important thing is whether the prompts or instances that you're seeing themselves are adapting to your earlier decisions. So I might pick the D based on the algorithm that is allowed. Okay, but the x's then get drawn from this D independently. So xt versus x1, there is no relationship other than independence.
I guess just thinking in terms of your application, like people doing like this adversarial attacks on the ChatGPT or whatever. Right, it's not entirely obvious which of the two is like the better model for that in some sense.
I would argue that this is definitely not a good model because this is about performance on a distribution. So,
But there is a distribution, so you have adversarial theories you can make after the model is fit, right?
but that keeps changing. So that's the issue. So here, if I look here, this by definition has this has fixed the distribution, the benchmark, right? Because XTYT came from the distribution. But the other one is the one that's not fixing, and it's just saying for any adversarial queries that would have been asked. So there is a slight difference. Maybe let me actually introduce that model because I don't think everybody has seen it yet. Okay, so what is the model I want you guys to have in mind is that there's no longer any actual distribution. There's just an adversary who creates these prompts or XCYTs. And what the learner wants is to achieve a good performance over this sequence that's being generated, okay, no matter what that sequence is. And if it can do that, then what you kind of think about is that this means that that learner was somewhat robust to what adversarial reactions of adversarial feedback loops and evolution of data. So this was where we started for the stochastic setting. What changes when you think about adversarial is that there is no distribution D. Everything else remains the same, except that now the world has to pick XTYT, and it picks it adversarially by thinking about the full history of the past. So both earlier decisions that algorithm had, but even earlier prompts. And these prompts are actually, it's important because that's how you find weaknesses of algorithms and also in fact fool these algorithms by kind of adaptively working with them. Everything else remains the same. We're still going to talk about average regret with respect to the best fixed classifier. You asked me something that I have a hidden slide for, but I don't know if it's easy for me to bring a hidden slide. Is it easy to bring a hidden
I
slide?
have no idea.
Maybe I will. Okay, I will maybe skip the hidden slide and just tell you that there was this question of while XTYT is adversarial, I still have an H star that belongs to a fixed class. I want you to remember the stochastic setting because it was exactly the same thing. In the stochastic setting, we said that H star was the thing that made sense for the distribution, and that's what I'm trying to compete with it. For the adversarial setting, you can still think about it that way. You could kind of think that maybe my H is really large, and typically it is quite large. Another way to think about it is that, yeah, if it's expressive enough, there's truly something here that would have made sense. That might have been even human common sense, who knows? And that's the thing I'm trying to compete with. But that's definitely true that now it does matter, now and before, it does matter what your H is representing. What was the question?
Yes, I can also imagine, and it's sort of just simply covered by this framework as a bit of benign adversarial prompting. In fact, I think that's really what's mostly being done, as I understand it, with in order to fine-tune these large language models, they go to this kind of stage of some very carefully hand-picked plots, which and then they're making contrasted learning.
Maybe waste 10 minutes.
Okay, right.
I want to talk about some benign adversarial modeling and then tell you why, in particular, fine-tuning is a bad way of doing it. But I mean, that's not something. Catch me offline about the fine-tuning, because I'm not planning to go into that. But I will tell you, at least we have a pretty good understanding of how to make these models fail. And part of it comes from fine-tuning being a bad idea. Like not the right idea, or it's like a band-aid idea. Okay, so I think I touched this. No? Okay. So let me just highlight why the adversary's power is quite different here. We are still working with the same class of these like intervals or thresholds that I called. But I'm going to tell you like this like hypothetical game or hypothetical sort of prediction problem that the adversary can play and make it very difficult for the learner to learn. So what is this hypothetical? The learner has to predict the label of whatever the adversary gives it. So the adversary starts essentially by doing some kind of a binary search and playing on that tree. So it starts with a half and tells the algorithm predict whatever way you want, plus or minus. The algorithm can decide whichever. Whatever it does, the adversary pretends that that was a bad idea. And it says that, oops, you made a mistake. Actually, the correct label was plus. Let's continue this. And he'll ask the next question, 1/4. And then the algorithm again wonders whichever way it goes, the adversary goes the other way, and other way, and other way. And at the end of the day, the adversary has made sure that there was an H star in that class of H that was still consistent, okay? Why? Imagine that this is the threshold HA. Anything on this side should be positive, and indeed it is. Half was labeled positive. It was claimed to be positive. 1/4 was labeled as negative. 3/4 was labeled as negative. So everything on this part of the line is indeed negative. Everything on this part of the line is indeed positive. So even in this like super very simple class H, the adversary, by just kind of adaptively deciding where to ask questions, made sure that, and it could have gone down any which way, made sure that the algorithm was forced to make an error on every single round. And at the end of the day, the best classifier would have made 0 mistakes. So this is a toy example of why learning becomes so much more impossible as soon as you allow adaptivity, even if you limit yourself to a very simple function size. So I told you how to think about VC dimension, even though its definition wasn't important, but as the characterization of learnability in the vanilla setting. And the reason I wanted you to think about it that way is to show you that that utterly failed in terms of thinking about learnability in the adaptive setting. And if you were already worried that VC dimension of something like neural networks is large, you don't even need to go there. Think about thresholds. VC dimension is small. Still, there's something else that's large. What is that something else? It's called the Littlestone dimension. Again, keep it in mind for 5 minutes. Doesn't really matter what it is after 5 minutes. I just want to show you that it's different. The idea is that the role of VC dimension, first of all, it's not sufficient because the thresholds had VC dimension 1, and we saw that you cannot learn it. But VC dimension is really about labeling an existing set, whereas we're working with these trees. So this is not really an existing set. It's more about paths that you can take down in a tree. So what Littlestone dimension is, which is the thing that characterizes learnability in the adversarial setting, is a full decision tree. Think about it. And the right way to think about decision trees is that I have my nodes being different feature vectors, and then my edges are plus minuses like right, left, child. And then paths are defined by these plus and then minus in different places. And Littlestone dimension is the size of it's the height of the largest tree, where every path that you can take is consistent with one function in your function class. Okay, so this is consistent if there is a function that would label this point negative and this point positive. And that definitely exists in the example we had, because that's literally the way we showed you that, no matter where you do plus minuses, there's always one function that would be associated with that leaf of that tree, that path that's consistent with the whole path. So the Littleson dimension of this example is infinity if you allow your adversary to give finer and finer and finer x's. Okay. So what we just saw is that thresholds have BC dimension of 1, Littleson dimension of infinity. In fact, almost any ML classifier set that you think about has a Littleson dimension that is infinity. Because anytime you have a thresholding behavior, has an impossibility of learning associated with it. It's sad, and it's not only a hypothetical problem. Everything I tell you, which is about adversaries, actually applies to privacy. In fact, whether or not you can privately learn is also defined by finiteness and Littleson dimension. So these are concepts that are not just hypothetical, they're actually coming in societal needs for the types of guarantees you want to give for either robustness, privacy, or some other stuff.
So can you explain the privacy thing a bit more?
It's a different kind of thing to open. All I can tell you is that if you want to provide differential private guarantees, it's a form of privacy that says that I can rely on learning from many samples and kind of protecting individual identities. That can only happen with if the classifier set has finite roots. It's actually related to even notion of regret. You can do it if and only if you can have good regret.
On the topic of privacy, I've seen some people suggesting to use GANs to do differential privacy, but as you mentioned, like there's very little we understand about vanilla neural networks, let alone generative adversarial neural networks. So how do these two parts happen at the same time? We don't understand them yet. We use them to differential privacy.
There's a lot of stuff in learning that people claim things and they just don't hold. And a lot of times it's okay because it's about, oh, can I tell apart ships and trains? And if I didn't tell them apart well, it's not the end of the world. But there are certain things that you need guarantees for. Like if you say that the US census data is private with blah, blah parameters, that better be private. There's legal standing of what that privacy means. Can you do it with GANs? Absolutely not. Can you do some things with GANs? I will talk about GANs are very related to what I'm talking about. I wasn't planning to mention them. There are situations under which you can get guarantees from GANs because you can get no regret guarantees. And that's what we're going to be focusing on. In fact, even for privacy, again, I'm not going to mention it. I will talk about the benign adversaries, and there's a notion of benign adversaries in privacy for which you can provide private guarantees formally mathematically. So, yeah, but in terms of how do you justify people claiming things and then them not working in math, that's very common in ML. It's okay a lot of the times. Unfortunately, not a lot of times where we truly care about that.
That's a little bit to Jan's question, right? Like when we actually care about the worst case, and many cases we don't, because it's not the relevant case.
Yeah. Yeah, I would say for privacy and robustness is slightly different. I have some bigger questions that I want to open up at some point for bigger discussion. They are less mathematical and more about identifying what type of robustness you don't want for what applications, which I think is the right way of formalizing this, because we're going to see that these impossibilities are truly there. So we need to figure out what is it we want. Let me skip this. It's not actually very important. I wanted to just give some other examples of Littleson dimension. But the main thing is that now the second takeaway is that while BC dimension sort of characterized learnability in the vanilla sense, Littleson dimension, which is always larger, at least, and most of the time infinity, unfortunately, is the thing that's characterizing other things we really care about. And the reason for why Littleson dimension is a lower bound is actually these kind of adaptive processes that truly zoom in one location. And the reason that it's an upper bound is that there is still some notion of that proxy, that coverage. It's just not for distribution. It's for something underlying. So it's more actually about the trees and the leaves of trees. So there's still some notion of that. And little summation is the thing that's going to characterize it, but we're not going to go into that. So what's the TLDR here, really? The TLDR here is that you should really be thinking, if you're happy thinking about vanilla learning as easy, which I want to encourage you to think about that because that's the easiest setting in this talk. The non-vanilla, let's call this chocolate one, is impossible with the adversarial thing. So where is that coming from? And I thought, especially given the econ audience in the room, I thought it's nice to actually connect this back a little bit to the min-max and max-min and min-max theorem. Not to say anything necessarily very surprising, but to show you some frontiers of research in case you want to then, as people interested both in CS and econ, to look at. So we're going to take a little step towards thinking about zero-sum games and thinking about notions of equilibria. There's no longer a learner and an adversary, just think about two-player games. And the basic setup of two-player games. But if the first role player was kind of playing hypothesis, then his actions were going to be these functions. And if the column player was taking XYs, then his action is going to be XYs. And they both get payoffs. This is really that loss that we're talking about. Since it's a zero-sum game, I'm just going to refer to the role player's utility, penalty as a loss. And that's the other guys. Minus utility. So we know that there are solution concepts, again, because I know that there are people who might not know game theory also in the room. So let's do a quick recap of that. A mixed strategy refers to like when you pick a distribution over rows or columns. And you could sort of think about the loss of your mixed strategy would be just like the expected loss if you took your action from that mixed strategy and your opponent did the same thing. So here it would be sort of the expected loss. So there's two ways to think about these games. There's the learner or the role player going first, or the column player or the adversary going first. Let's start with the column player going first, what I refer to as max-min. What this really means here is that if the adversary is going first, he's choosing a distribution over all the possible distributions. And then the learner is trying to choose a good predictor, good function that would minimize this loss. So what this really means is that you should think about it as maybe the adversary is committing to a distribution. It will commit to a hard distribution. That's kind of max what we were asking. And then after the adversary has done that and it's been fixed, the learner goes and finds a good function for that distribution. This is close to what we were talking about in the stochastic case, especially the worst case of stochastic, where bad distribution is chosen and then the learner has to figure it out. What is the min-max perspective?
With large sample version of that, right? We have a lot of problems.
Yeah, there is no samples here. This is just kind of the exact game rather than the stochastic game. It's like the benchmark. The benchmark, if you know everything. What's the min-max version? The min-max version, the learner goes first. You should allow the learner to pick a random classifier because lack of randomness for the first player is always a problem. So, but that's okay with us. He'll pick a random classifier, and then the adversary picks an XY that's bad for that classifier. So that you can think about it as the learner committed to some random function, and then the adversary picked a difficult instance. What I'm claiming is that while this is not our setting, this is the connection between these two is very related to the same question that I asked you guys to think about just 5 minutes ago. Can you have a no-regret algorithm in presence of an adversary? Now, we know that min-max and max-min are actually the same under some conditions. The typical condition is that the action class is finite. Forget for a second that nothing is finite in machine learning, especially not age. But imagine that this was this. So if I had finiteness in fact they're equal, and there's many ways to prove this, but I actually want you to at least be aware of the fact that no regret algorithms is one way of proving this claim. How? You kind of think about, we thought about max-min as the stochastic case. You kind of think about min-max as being very related to adversarial learnability. In fact, the reason these two become equivalent is because I can imagine a hypothetical dynamics between my first and second player. My role player, who's the learner, is going to do her round, have a no regret algorithm. As in HT is decided based on a no regret algorithm compared to the H star, the best H star in class.
Which we can have since finite support means finite Littlestone dimension.
Finite support certainly means finite Littlestone dimension. Finite H means finite Littlestone dimension. Yeah, so if I had finiteness, that I have a no regret algorithm for. The column player does something even simpler. So just her time step takes a pair of xy that's bad for H. There was a question about GANs. This is very similar to how GANs are trained, slightly different distance metrics. And if the two of them do this, what happens is that the average HT that's played here becomes a min-max strategy, and the average XY that's being played here becomes a max-min strategy. So that's actually how you can prove very easily that min-max theorem holds. But as we said,
so maybe know this min-max also goes through under much more general conditions, right? It's like if the L is like convex concave,
right.
whatever.
So I did this thing which I essentially linearize min-max because I'm talking about expected. In fact, for the version of learning we are talking about, expectation is the right one. For GANs, there are different losses.
But so what would that imply, that if it goes through for these more general cases with convexity, concavity?
It doesn't imply much, but I'm going to just tell you, just wait 3 minutes. I'm going to tell you this other thing. Okay, so what is the challenge of min-max? We can't really use it because the conditions, at least the way I told you, doesn't hold. So the question that has been asked and very recently has been only answered is, then what characterizes min-max, max-min being the same for general? So yes, convex concavity with compactness like works, but that is not sufficient for learnability either. Compactness is usually the thing that fails. But what's the role of no regret? Especially because I showed you that no regret would have, like, that's the way I proved min-max theorem. So it feels like if I have a no regret algorithm, anytime I have a no regret algorithm, I already have min-max holding. And we just said if Littlestone dimension was finite, I have a no regret algorithm. Okay? So it feels like what I've already told you is that if there is a no regret algorithm, which certainly there is under Littlestone dimension, then min-max theorem. Turns out there is a tiny subtlety, and that's why this problem wasn't solved 20 years ago and it was solved a year ago or 2 years ago. And that subtlety is a tiny difference between what it means to play a game versus what it means to learn. If I play a rock, paper, scissors with you, I, as the learner, limited to playing rock, paper, or scissors. I cannot invent a new thing like, oh, I have tank. And all of a sudden, tank is all powerful. But actually, in online learning, that's not necessarily a restriction. While the function class is limited, you're allowed to come up with functions that aren't in there when you're classifying things. In fact, if I go back here, where should I zoom in? It's this part. In particular, I used FT rather than H to emphasize that F is not necessarily part of H, okay? When it is, it's a special case. It's called proper online learning or proper learning, when FT also has to be in my class H. Proper learning is slightly harder than improper. It is harder than improper learning. But that's the reason they claim that there was a no regret algorithm wasn't sufficient to show that min-max theorem held.
It's improper learning, we can somehow convexify or mix or
The worry is that it's not just mixing. If it was mixing,
Like
it would have
it's
been fine because it would have still been a mixed strategy. The worry is that it's just not at all supported on the rows anymore. That was the worry. Yeah.
So just to understand a bit better this setup of improper versus proper. If I'm actually trying to solve whatever classification problem for the sake of the argument, I don't even think about there's a best in this. Like I have to consider a class of functions. They don't live in the vacuum, so there's a class, whatever that might be. So when I'm doing that, I'm not even thinking about what is the best inside that class. I just want to minimize over this set. I don't see how suddenly this lives in the vacuum and now this. How can I have that or two classes of functions? How can I have these and these in a general?
I can tell you how you can do this. So forget about H for a second. Like this could be the class of all neural networks of certain size. Okay. What might happen is that when you get XT, YT, you don't define it as parameters on the network anymore, but you first cluster your set, and depending on where X lies, you apply a different neural network to it. Okay. So it's kind of like you pre-process your X. You have figured out that it's really hard to learn a good neural network, but you've actually figured out if X falls in some set, then it's much easier for you to first like get it to go in that set and classify it using some neural network there. And then maybe pre-process it in a different way and classify it using a different network. Now, it doesn't mean that you could have put those two networks together and achieve a good classification within this class H anymore. Okay.
Okay.
So this is kind of prediction that's a lot more dependent on the actual X than your neural network might have allowed you. It's a little bit subtle.
Okay. So, but then if what I'm considering is this new class of combination, not convex combination of multiple neural networks, then I'm working on that space and now I have this, I'm going to call it HPIC. So
the concern is that HBIC might be a lot bigger.
But isn't there a way to have H big be H and then H small be a subset of something like, so to make the H big be the set of neural networks, which is what I'm actually considering, and compare it to someone else so that it can.
Well, let me just tell you the answer we're after, because as I said, this was resolved about 1.5 years ago. The way that it was resolved was to show that the main challenge was that when the little stone dimension was finite, we knew algorithms that had good regret, but they were very X dependent. And the way that this was fixed was to show something. Let me see if I ever mentioned it. I don't think I mentioned it. The way it was shown was to show how you can make that algorithm proper. And how was it made proper? It was a way of saying that while it looked very X dependent, in fact, it had a finite support. It was a finite support mixed strategy. Like there was a way of writing it as a finite support mixed strategy. So you're not changing what your H represents. It was more like you algorithmically changed how you use finiteness of little stone dimension to talk about things that actually look like mixed strategies rather than something that looks very abstract, X-dependent type of classification. Yeah. But again, I'm not going to go into the detail of that, in fact, but if you are interested, this is the paper. Okay, so about 2 years ago. That said, something more interesting than I already said, that little stone is sufficient for min-max, but it's actually not necessary. And I think this is interesting because min-max being slightly requiring weaker assumption than like full adversarial capabilities is actually quite interesting to me. And I want to tell you why it's slightly different. So actually the thing that happens to be the characterizing thing, especially if your game was 0-1, if it's real value, it's more complex, is something that looks like little stone dimension because it looks like thresholds. It's something called the triangle dimension. And it essentially says that if you could move your columns around and rows around, so that you had an upper triangular subgame that was of infinite size. Then the largest upper triangular subgame that you could make is the complexity of learnability of min-max. And if it was infinite, then you cannot have min-max. If it's finite, you will have min-max. And this looks like little sum dimension with one subtlety, which I only put here for those of you who are super interested in this. We're not going to go into it. The subtlety is that little sum dimension might be large because you can come up with different bigger and bigger trees. This subgame thing is only large if you can grow the same tree a lot. This is something some people in stats sometimes refer to it as div. There are two different notions. So little sum dimension being finite is slightly stronger than the triangle dimension being finite. And this is the thing that actually characterizes min-max. So it's still related to no regret, but slightly weaker. What's the takeaway I want you to have from this?
Do you have examples that fall in one class but not the other?
I do, but because of the limitation of time, I don't have it here. It's one of the hidden slides. Let me tell you the thing that I was going to tell you at the very end. I gave a 4-hour tutorial that's online on YouTube. Went into details more about these things. So you can watch that actually if you have some of these questions left too. The takeaway here is that in general, learnability is very sensitive to the actual adversarial assumption. Like adversarial learning and zero-sum games look so similar, but they're still a tiny bit different. And obviously there was a big difference here. There was a question about benign adversaries. I think it's very interesting. And I'm going to give you one example of this, mostly as a motivation for why this should be studied. So we've talked about stochastic, we've talked about adaptive adversaries. And the point I want to make is that we need to be rethinking what adversaries we actually have. And there are some good aspects to this, like having an adversary that's somewhat adaptive is a very reasonable thing. If we are going to be worried about feedback loops, unpredictable ways that things evolve, it's very natural for future things to depend on the past things in ways that was unpredictable for us. So that I want to continue capturing, the fact that whatever is happening to the data is an adaptive process rather than an independent process. But there was some kind of like a quirky way of modeling this, which also allowed the adversary a lot of power. Like in that binary search tree, the adversary could go as deep as it wanted into the 0, 1 and make instances that were very precise. And that seems to be more of a quirkiness of the adversary rather than actual property that we want to capture. For example, here we are saying the adversary can create any instance without any sort of cognitive or difficulty issues. It also means that it can do exact measurements of X. It knows how it's represented in the internal, ML model in some sense, so it can make exact representations. It needs to have no shaky hand. It needs to know a lot of stuff. And this seems stronger to me than needed in many applications. Certainly for GPT-4, we know very little about GPT-4 and how its internal representation is working anyway. So it's very unlikely to need this, to have these strong amount of knowledge. So what I want you to think is that there is some kind of a noise, there's some kind of a randomness that's impacting the adversary. And there's different ways of thinking about it. We'll formalize it with one model, but you could kind of think about it as that, oh, there's no real adversary. It's just unpredictable things that happen in life. And I want to be quite robust in these unpredictable things. But it's not very exact. Like maybe different people enter different types of feedback loops because they react to me differently. And that's sufficient to sort of smooth things out and make some noise into how the data is actually observed. Or you could think about it as noise and lack of precision is inherent as part of how the adversary interacts with the model. Like maybe the adversary is in a physical domain, like an audio video domain. It's actually trying to, change pictures that you're taking, your self-driving car is taking from stop signs and things like that. And there are mismeasurements, there are angles that are never exact, there is sometimes dust in the air, the light is different, doesn't have full control. And the third way of thinking about it is that lack of precision is not really part of the adversary, even though we think about it as part of the adversary. It's part of the data collection training by design. And this is another part that when we talk about why privacy sometimes is more doable is because we already design our groups to be coarse. Like we don't ask how old you are up to the date of your birth, really, but we ask you, are you in the age group of 18 to 25 or not? Your income bracket rather than actual amount of income. Zip codes in the UK are pretty exact. In the US, they're all over the place. So that's part of the design. So what's one nice way of capturing this? We call this the smoothed adversary. For those of you coming from computer science, you might have heard of smooth analysis as a perspective of capturing these things. So that's kind of where this name comes from. Things look as before in the sense that you have a learner that's predicting, but now instances kind of come from a world that's somewhat adversarial and somewhat random. And we say that in some sense, what the adversary is doing is picking sigma smooth distributions, dt. So there's still dt that depends on the past, so that's the adaptive part. But the distribution is smooth in the sense that it's not exact. It's not focused on one point at any point. It has to have some non-trivial amount of support. You can think about it as its max density being bounded so that it's not arbitrarily focused. And then we ask the same kind of questions. Another way to think about this is that maybe adversary picked some XY and then the world perturbed it. So that depends on which kind of those three things you were talking about, you like to think about randomness anyways. So what happens here? This is the part I'm going to skip any of its proof because we won't have time. But I do want to tell you what interesting thing happens to the image of this landscape of results. When we had adversarial learning being impossible, that's as if I have no perturbation absolutely, like sigma is 0. The density can be arbitrarily large. You can focus on any one point, okay? When things are stochastic, it's a subset of having maximum perturbation. Like if perturbation sigma is 1, in fact, you're kind of like either a uniform distribution or any fixed distribution. And that's exactly where you're seeing little stone dimension versus VC dimension coming in. And we said this is impossible, this is vanilla easy. And what you can show is that if you have smoothness in your adversary, you're actually closer in terms of bounds to the vanilla setting. Whereas in terms of capturing adaptivity, you're closer to the adversarial setting. So what do the bounds look like? There's still that VC dimension divided by T, which is pretty good. There's, of course, the magnitude of noise coming in. And that's going to be logarithmic in 1 over sigma. That's the optimal bound.
So it's just like the adversary saying, okay, I think you're quite good at many parts of the domain, but these particular types of example you're quite poor at classifying. So let's really hone in on those. Not actually trying to really trip me up, but just give me loads of examples in a region where I'm there, right? I tend to kind of make false classifications.
Right. One way to think about this is that if the adversary can find things that are bad, then it's a very generalizable thing he could have done. As in, it's not a very particular thing that he found. There was a significant subset of things that you were underperforming on. And then he focused on that.
But like he's been regularized.
He's being you can think of it as he's being regularized. I think that's fair. Perturbations are very similar to regularizations.
So this is super interesting. I mean, I guess here, right, sort of the constraint you put on was sort of in how much the distribution can be distorted relative to some base measure. I guess a different constraint would be sort of how quickly it can evolve over time, right? So I'm not sort of constrained relative to some fixed target, but basically T+1 relative to T, the density can only change by so much incrementally. Is anything known about that?
There are those that are studied as well. They're not as nice. The bounds I know aren't dependent on VC dimension. They're dependent on the distance the difference between the distributions on their marginal distance, which could be quite large. The nice thing about BC dimensional coverage is that it's it doesn't depend on the domain size, whereas those things do. So there are, what I'm saying, there's weaker assumptions that get you this, but not exactly the one you're asking.
Can maybe just bracket open like a slightly bigger discussion here.
Yeah.
Because I feel like all of this is framed in terms of we take the side of the algorithm designer and are worried about the adversary. But at times we might actually want to think about the opposite. Let's say there's a dictatorship that's, or whatever, some other powerful actor who's deploying some system for surveillance or control. And that in those settings, you might actually like the difficulty of adversarial learning in the sense that it opens the possibility of persisting in systems. But I would say, I don't just think of things like face recognition and people using like face paint to mess it up, or right in a way.
I think that's an interesting way to say it, like thinking about.
It's the same, but it's kind of flips the interpretation on its head on what we like in some sense.
Yeah, I want to emphasize something. I think that's very interesting what you said. I want to emphasize that the fact that the adversary can do this doesn't mean that he can do it very easily. Okay, computationally speaking, there is still overhead. So that's another interesting question, actually, I was going to pose that I think matters, especially for the things that you are thinking about.
But there is in a way like of this built-in value judgment whose side we take in these systems, right?
Yeah, just quickly following up on that. So my talk is going to essentially about that.
Cool. Okay, so this is the part I'm going to skip, and since I can't access my slides, I'm going to skip this way, sorry. Okay, so kind of the takeaway picture I wanted you to have from there is that if there is this type of adversarial assumption that we're making that's more benign, we are essentially getting rid of the worst aspect of impossibilities while keeping the adversary still pretty natural and adaptive and realistic. And I think the takeaway message here should be that while we do see these learnabilities being quite sensitive, sometimes it's sensitive because the definitions themselves are so brittle that they require us to reevaluate those definitions. And some of these more general questions is that the bottom line is that we cannot protect against every type of misuse. And it's important to figure out what type of misuse is actually the type that we should be really worried and focused on. And I think this is very dependent, of course, on the domain. For example, I think platform versus services are quite different from each other. Like misuse by content creators on platforms can actually impact users a lot more than it's like users who are then going to be exposed to that harmful content. But an individual using a large language model to access information that would have still been present somewhere on the net, but now maybe slightly more easily accessible. And if that individual was so intent on doing this misuse, it seems that the harm is slightly at a different scale. So I'm not saying that we should be taking sides in this room right now about which one is what, but the main thing is that we need to discuss sort of the actual robustness guarantees that we want, because we cannot provide all of them. And I think statistical validity and kind of having a misuse that invalidates that is actually pretty important. And that actually falls more closely related to platforms versus the language models that I was giving you. There was a question about fine-tuning, which I said I want to talk about, but let me just say that the common approach to limit misuse is amending data sets with examples of misuse. Fine-tuning is one way of doing that. And this happens to be an inherent failure mode for safety, at least for large language models, because your data set that you train on is so many orders of magnitude bigger than the data set you fine-tune on that it's very easy to sort of turn off different parts of your model. What I was gonna say is that, to me, even loosely defining safety goals can be implemented, I think, more effectively than at least ad hoc extensions of data sets. I do think that companies are actually thinking about both of them. It's just that these things aren't being released to us necessarily. And we're just imagining what kinds of data amendment has happened. Okay, so I know that we're pretty close to time, but I did want to go beyond. Yeah, 20 minutes, yeah, but still, this is not quite half of the time, but still substantial.
Okay.
I want to talk about going beyond adversaries here. And sort of thinking about more interactions that are strategic, but not necessarily for the purpose of kind of causing harm, but because you're sort of self-interested agents. We're going to go back briefly to the game model, but think about general sum games rather than zero-sum games. And kind of the main thing here is that we do know that once you have general sum, the min, max, maximum, they're not the same, they're not the Nash. Everything now matters in terms of who's going first, who's going second. And of course, that's kind of the commitment value. Even for mixed strategies, kind of you can think about a Nash equilibrium in this game. In fact, dominant strategy is for the row player to play up. And then as a result, the column player would play left and the row player would get 1. Whereas if the row player wanted to commit so that it wasn't stable, but it was committed, he could have played down and then let the player respond with right and then get 2 here. In fact, the optimal commitment would have been something in between where you do almost 50-50 for commitment to a mixed strategy. So we are going to be talking about commitment and its value a little bit. I want you to have both mixed strategy commitment and pure strategy commitment, mostly because I'll give examples that kind of refer to both. So what that means is that player 1, leader, sometimes I say principal, sometimes I say leader, player 2, follower or agent. Player 1 commits to a strategy, player 2 best responds to it. And then the player 1 is interested in optimal commitment. Similarly, you could have defined it for the pure strategy version of this, just analogously. And what we do know is that obviously committing, if you can, is advantageous to the leader because it's relaxing the solution concept compared to Nash equilibrium. This is something that you also saw in Celestine's talk on Monday, where there was optimality versus stability, which is exactly getting at the same point. So why do we care about commitments? I want to give you 3 examples of applications that we care, especially in learning and for statistical inference, and kind of use them as motivation for what you're going to study next. One is thinking about how to spread your security resources. This is especially about mixed strategy commitment. You sort of think about sophisticated attackers kind of like try to attack the weakest point of any system. And then you want to protect targets that are of the highest value to you, but conditional on, of course, how the attacker is going to attack things. Here, the defender or the principal, the leader has a set of resources and how for protecting targets and how he spreads his resources to targets is a mixed strategy. The attacker sees a set of targets. It's not a zero-sum game because things that are valuable to the defender are differently valued by the attacker. Especially true in poaching, where the most endangered animals aren't necessarily the most useful to the poachers. So you want to kind of think about that differently. There's ride-sharing platforms where the ride-sharing apps kind of use predictions about supply and demand to decide on the pricing strategies, how they map to prices. And there's a lot of different types of manipulations. Rider manipulate usually by, I mean, they have competing platforms and they can switch, but they also manipulate by changing the location of where they're requesting rides or changing the time and length of how much they're willing to wait. The drivers also manipulate a lot, actually, by turning off and on their apps at strategic times and strategic locations, usually around airports. So that all messes with the algorithm. You can think about it as X as being high-theme policy, then Y as activity on the platform. And again, these are not zero-sum. It's not adversarial, it's more self-interested. The last one is strategic classification. Celestine also gave a great example of this. You're kind of thinking about how you're making decisions based on some observable attributes of applicants, and applicants can try to change them. And then you could sort of think about the learner or the principal trying to choose between a set of classifiers, and then the agents responding to that set of classifiers by manipulating their data. Again, not zero-sum. In fact, this could be that different players respond differently because they are starting from different points as well. Out of these, this security game is the mixed strategy. The other two are usually pure strategy in more structured spaces. Now, what is optimal commitment and how do we find it? The nice thing here is that for most of the applications we care about, especially when it comes to learning, there is some structure already that that is kind of underlying this optimal commitment. And in fact, once I write the optimal commitment, it's like a simpler maximization on a single function. And this function tends to have certain properties. In the three examples I gave you, it tends to have piecewise linearity or piecewise Lipschitzness and concavity. So in security games, for example, you can think about the space of your strategies, your mixed strategies as like probability vectors of how you're protecting different animals.
So I'm just not entirely following the notation here. So you're switching from these strategies to pure strategies?
Oh, it's I'm just saying there is both. For this is pure strategy. For these two, this is mixed strategy. For these two, it's pure strategy. Yeah, so here, like you have a pure strategy, mixed strategy, which is a probability vector of what probability you're protecting elephants with what probability you're protecting gorillas. And each point here will induce, an attack. So if you're protecting gorillas a lot and not elephants, then elephants are likely to be attacked. But then this is piecewise linear because, in fact, in each of these pieces is linear, because once I think about elephant is going to be attacked in this area, the utility of the defender is just what was the probability I protected elephant. So it scales, it's like a linear function of the mixed strategy. So you have piecewise linearity here. For pricing policies, I'm not going to give you an exact example, but there's usually diminishing returns in revenue. So if you think about just increasing the price, usually what happens is that to a degree, you're just getting more revenue per person, but maybe slightly fewer people. But then at some point, you're losing your mass of people who were willing to pay. In fact, revenue curves, not in price, but in quantile, typically are concave. For classification, some soft truncation is the most common thing that you see. I really liked one of the examples that Celestine also gave you, which kind of looked at this. I think it was the Columbia poverty index, right. This is more about reported income, but very related, where you start with a distribution and then you classify people as, well enough off and not well off. And then based on the policy that you make, you see that the distribution gets reparameterized and slightly truncated. So all of these are nice properties, and the niceness of these properties actually helps us with learning them. Because what happens is that we typically kind of know what our utility is as a principal. Like I know, I'm trying to maximize revenue maybe. But what we sort
of you might take the side of the riders or the drivers like that with the platform.
You could. In fact, I will tell you something in a few slides if I have time. There's if I have time questions. Okay. But we are going to take the principal's perspective because I'm thinking about commitment. You could always change how stubborn the principal is versus the agent is and switch the commitment. So if you want to change it. But mostly the principal is the one who has the control. It's the longer living agent is the one that has more patience, more resources, the one who can actually commit So whoever that is, let's take them to be principal. And what happens is that the principal might know its own utility, but certainly there's a lot more uncertainty about what actions or utility the agent is playing, or why is agent doing certain types of actions. Even if I see its action, why exactly, what was the utility, what was the reason? So while we could actually talk about optimal commitment, we cannot really figure out what the optimal commitment is until we understand what motivates an agent to respond in a certain way. So what people have been thinking about, especially from computer science part, is to think about figuring out that crucial aspect of how the agent is responding or what the utility is by repeatedly interacting with the agent and seeing its responses. So what that look like is a definition called Stackelberg regret. And what this definition is very similar to regret the way I defined it before, in the sense that you're still trying to compete with the best strategy, but the way you define the best strategy is slightly different. You say that I look at the commitment value of that strategy. So what would have been, in fact, the optimal commitment value for the principal? And then you say, okay, well, I didn't know what my optimal commitment would have been, but I kept interacting with the agent. And maybe this is what I saw, because every time I made some action, the agent responded, specifically best responded.
You're saying this only makes sense in non-zero-sum games, or is this also interesting in zero-sum games?
It's interesting in zero-sum games, but not beyond external regret as much. It's more interesting in non-zero-sum games. I put a T here just because you can allow the actual utility to change over time. And I will come back to the Stackelberg regret a couple of times because I think it's important to both understand it and criticize it. But first of all, how is it different than external regret? And the question of, is it only interesting in general sum games? What I defined as regret earlier is also called external regret. And this kind of how the algorithm performance is actually defined is not that different. Especially if you remember in the proof of min-max theorem, what I did was to say that, oh, the adversary at every time is best responding. That would literally be this, okay? And I'm saying that maybe in the Stackelberg, it's also best responding at every time. The difference becomes much more important about what is the benchmark for them. So for Stackelberg, as I said, is the principle's utility for the optimal commitment. What external regret is talking about, especially in a commitment world, is a much more hypothetical thing that says that, well, the responses of agents historically were induced somehow. And I'm going to assume that they remain the same and somehow evaluate my action over the historical thing, rather than what kinds of reactions it will induce in the future. So that's the difference between the two of them, okay? In fact, that's kind of the regret version of talking about stability versus optimality when I was talking about Nash versus Stackelberg or commitment. In the sense that we understand well that in the just like one shot, what's the value of commitment? There is a value to commitment. In this kind of a many shot online setting, there's also an incompatibility between these two notions. In the sense that if you want Stackelberg regret, you may not, like no Stackelberg regret, you will have external regret in the worst case, and vice versa, okay? And this is not that hard to see why that's the case, again, because stability and optimality are different from each other. It's like the whole point of committing the Stackelberg optimal commitment was that it's not a best response to the history. That's the whole point of the advantage you get. So you shouldn't be giving that up. And external regret doesn't at all actually account for the fact that the followers will also adapt in the future. So that's why the difference between these two continue to remain. And it's important to know which one of the two you're after. I will argue that in most of these more policy or learning related settings, you are after the Stackelberg no regret, but you need to justify the existence of your external regret, because that's how a lot of people would evaluate you.
So external is almost as if the commitment was fixed, right? Besides.
Not necessarily, because it's more of a historical commitment. It's not, neither player is committed. I think about it as actually stability.
Goes to Nash.
Correlated with equilibrium. Okay, I wanted to say a little bit about how you find optimal commitments. So if you are after the Stackelberg game, it's still equal to external regret of some completely different function class. That's not hard to see. You just write this as a function of complicated function of just your action. And now what we had about the piecewise linearity, Lipschitzness, concavity, that's kind of where things start to rescue you. Because all of those properties are properties that allow you to learn more effectively. In fact, they allow you to learn even if you get very little information. This is kind of bandity information. What it means is that you never, you can only evaluate best response to a specific action you played. You cannot evaluate it to all actions you didn't play. So what happens is that you don't know your utility for things you didn't do. That's what it means to be banded. So in fact, a little bit more than banded, because not only you see the utility for the action you took, you see the best response. It's technically referred to as semi-banded, but we actually have algorithmic solutions that are tuned to the structure of piecewise linearity, concavity, Lipschitzness. I would say that there are somewhat ad hoc choices of algorithms. For those of you interested, I think there is a very much frontier style of research that somebody else can give, which is about, we talked about what characterizes learnability in the adversarial setting. What characterizes learnability in the strategic setting is very interesting and very open, because what characterizes banded learnability is much more subtle and much more open. We have mostly ad hoc algorithms rather than frameworks. With one exception of last year, there is a promising framework. It's still not a characterization framework, but for those of you interested, I think you should take a look at this paper. It's called the Decision Estimation Coefficient Framework. It is about characterizing statistical complexity of interactive decision-making. In particular, I think it's really interesting to think about, these are for arbitrary interactive decisions, how economic models of behavior would come into the picture with this DEC framework. Still quite new. If you're interested, I highly recommend you take a look at that. Let me end 3 minutes. Let me end by, I said that it's important to also criticize Stackelberg regret a little bit, because there is definitely a debate, at least on the CS side, and I feel like very related to what Econ has already addressed to some degree, which is how to think about repeated interactions, really, and rationality. In the sense, we think that learning from repeated interactions is somewhat antithetical to commitment, because commitment, the point of commitment was that you committed to something, you didn't change. It was verifiable, you didn't change, and that's where you took your advantage. Here, the learners aren't committing if they keep changing their strategy. In fact, they're committing to algorithms, but they aren't committing to per-step strategies. It has unintended consequences. One is that the agent might not be best responding, or might not even be capable of best responding if it wanted to. Maybe the agent.
It matters here if you think of the agents being the same one over time or different ones.
The fact, there is something about how fast the agent can learn. So if it's the same one, it can learn, but then it becomes more non-myopic too. So
but also I can punish you if I'm coming back in the future, which I cannot.
Exactly. So both of them are related. So actually the access of being non-myopic versus myopic, which is about how much market share you also have, like how often do you appear, is very interesting. And it does interact interestingly with how well you're picking up on the algorithm. So I don't want to go into too much detail, but I think there is one at least interesting thing I want to cover, which is that there's certainly a debate on what is the role of the principal, what utility even we should be aiming for. Is this optimal commitment the right utility? Is it the right benchmark? And I wanted to say that the reason this debate is there is because the agent's action actually really impacts both the agents and generally the welfare and the principal. In the sense that if the agent knew PT and best responded, as I said, the principal can get Stackelberg regret in most cases, so it can get us optimal commitment. But in many cases, because the agent doesn't know PT, it cannot best respond. And then weird things can happen. So for example, in the strategic classification, you might not know exactly the details of the current classifier in play. There was Karina's talk, I thought it was very interesting because the same thing, the fact that algorithms are so personalized, you do not understand exactly what that classifier is fully representing, but you might understand very little about it. For security application, the attacker wouldn't exactly know what the mixed strategy is. And for ride sharing, the people don't really know supply and demand. So the way that things kind of get sketchy is that if the agent, instead of actually best responding, does something that's much more historical optimization, like historical best response, or even a no regret map, you can get really weird behavior. You can in fact invert if you want, you can invert commitment based on the step size of the different no regret algorithms. It could give the principal too much advantage, in fact, because the principal can predict where the agent is going to go if the agent has very large step size. Very small step size, sorry. And then it can abuse that situation. It's also possible that the principal can't get its Stackelberg utility anyway because the agent is just super unstable in terms of how it's acting. So what happens is that essentially the theory of commitment becomes not very predictive when you think about algorithms that the agents might be using. I think here, and the next one is truly like the last content slide, is that while up to now, everything I said was mostly about notions of regret, and it didn't matter how you came to have that regret, something interesting here that happens is that the statistical judgment that you had underlying your regret minimization algorithm becomes the key thing in characterizing the utility. What do I mean? I mean, it's not really about regret or algorithm. It's why you chose your algorithm. So one example of this is that this is what I'm saying. The principal has some strategy in mind. The agent doesn't know it. But the agent, in a statistical sense, usually has a belief about this. Okay? This is a thing that no-regret algorithms completely ignore, or optimization algorithms typically ignore. They just say that it took some action. And then let's say that it's responding based on that belief. What you can see is that the consistency of that belief, or what the calibration of that belief, is the key characteristic. In fact, you can show that if the agent's beliefs were calibrated, the principal cannot get anything more than the optimal commitment. So it cannot abuse. In some sense, the principal cannot abuse a calibrated agent. And the principal can ensure to get this optimal commitment. So what this is really saying is that calibration, which is some common desirable notion of statistical validity, let's not go into what it means, but there are many methods for ensuring it.
It seems to connect a little bit to what Jan was talking about, right? Where unbiasedness is kind of similar to calibration.
Is unbiasedness similar to that?
I'd love to talk more offline about exactly what calibration here means.
Okay.
Yeah.
It's
But it's in a way like
this.
I mean, it seems to be of a similar flavor in the sense that there too, that the unbiasedness emerged as like out of this adversarial setting in some sense, as like an optimal thing to protect yourself against this adversary.
It works, it's nice, very.
And is this on every, is that at every time, that calibration property at every time step
No.
T or on average across?
On
the
average.
long run average across T? Yeah, so that is unbiasedness. It's a version
It's
of
unbiased.
So unbiased is over the sequence?
Right?
Sorry, yeah, it's unbiasedness of the sequence of beliefs Q for the long run average of QT for the long run sequence of PT, right? Basically, because you're saying the probability of the average probability of your belief matches the average probability of the true thing.
Yes, okay, but I guess a bucketed version, but not perfect. Calibration, but bucket wise, bucketed based on what the calibration is.
Oh, okay, got it. Right, bucketed based on
Because
the-
calibration, I'm not going into detail, but calibration always has bits.
Yep.
So it might be weaker than unbiasedness. It might be unbiasedness, a coarse version of unbiased. Okay, we should definitely talk about it.
Yeah.
But kind of like let's get to what it really means is that if you do not match the optimal commitment, it's either because the agent was deliberately actually not calibrated, which I take it as a lack of rationality or lack of strength, at least in terms of statistical analysis. Or it's because the principle wasn't sophisticated enough. It's one of these two. And it goes either above or below based on which one is overtaking. Okay. So this is why I think that while another computer scientist might stand in front of you and tell you that algorithms are the only things that you should be thinking about because we always think about them as the dynamics, I actually think that this is one good example even for computer scientists to stand here and say that it's not just algorithms. Think about both algorithms and the statistical judgment that was behind the choice of the algorithm, because they cannot be, neither one is sufficient to actually address the dynamics and the consequences of them. All we covered today was a very brief picture of this. There is a link to this 4-hour tutorial that you can use, or just talk to me and I'd be more than happy to go into the details of the things that I skipped a lot.
It's like good review paper for stuff.
No, I've been asked to write it and I've been lazy a little bit. Unfortunately, there is no survey, but there are we have scribe notes that covers a bunch of these things for a graduate course I have, and I'd be happy to share them. Okay, thank you so much. Sorry, I took longer.